Thanks very much. I'm honored to be here at the launch of what I expect is going to be one of the most important computing education research centers in the world. I want to frame my comments in terms of what we've already been hearing about the center. I'm going to give away my punchline first. Computing education research is hard. In fact, it's a lot harder than computer science research. And I'm going to try to lead up to that in the course of the next few minutes. So I think that this center is addressing some of the most critical challenges of giving everybody access to a very important new form of literacy, understanding the computing that affects their lives, and giving them the opportunity to be producers as well as consumers of this technology. I think that the scope is broad. Ages 3 to 19, formal and informal, this is huge. And explicitly, they want to try to reach students all around the world. How do they need computing framed in ways that make sense for their culture, focusing on equity, access, and inclusion? I love that they're grounding in the best practices of research, particularly in learning sciences, with an explicit design to impact practice in what they're doing. I'm also someone who sits at the intersection of computer science and learning science. I'm going to come to this talk today coming mostly from the computer science side. I want to talk to the computer scientists first and try to explain to them what makes these challenges so hard. So I'm going to start out with SNAP. I'm developing 2 new classes at the University of Michigan. If you're not familiar with SNAP, SNAP is a block-based programming language that is particularly good at manipulating media. And in this example, we're going to load a picture, a Big Ben, and then we're going to look at the pixels in that picture. So when you ask for the pixels of a picture, it comes up as a list of lists, where each of the elements is the amount of red, the amount of green, the amount of blue, and then the transparency in that particular pixel. And each of these varies from 0 to 255. So once we can have access to the pixels, all kinds of cool things are available, and we can do image manipulations. So I want to show you some examples from the SNAP manual by Brian Harvey and Jens Monig. So what we can now do is say that we're going to take the picture on the left and translate it into the picture on the right. And what we're doing is that we're going to make all the red parts of all the pixels, the first value 150. So what we're doing is taking all but the first of, so set the green, blue, and alpha aside, and just replace those first red values all with 155. And that makes the red picture on the right-hand side. Here's another one where what we're going to do is we're going to reorder the columns. So what was red becomes green, and what was green becomes red. So if you think about it this way, here's our pixels. We're going to move the green to that column and the red to that column, but we're still going to read it as red, green, blue, alpha. Okay, and so that gives us all the red parts of the apple turn green. All right. I was a little bit worried that this might be confusing for my students. SNAP is so powerful that it allows me to create new kinds of custom blocks, including new kinds of data structures. So I created a version of this first one where I can now say for each pixel in the pixels of Big Ben, set the pixel red to 150. So I'm going to plug 150 into all of those values. For the second one, what I'm going to do is I'm going to, where we were swapping the red and the green, I'm going to write a loop where I'm going to grab the old red value, move the green into the red, and set the green to the old red. So I'm achieving the same goal, that we're going to get sort of a greenish Big Ben. But the code is obviously different. So let's talk about these 2 sets of ways of thinking about image manipulation. The first one is functional. We've got immutable data. We're going to take one picture and we're going to generate another picture. We're using higher order functions like map. And computer scientists tell you that this kind of structure scales better, that we can run this across like multi-core architectures. What I'm doing, this second set, is much more imperative. It looks like we're doing mutable data. It's actually not underneath, but we're going to make it look like it's mutable data. And there's more lines of code. It's actually bigger, larger chunks of code. Which of these is better? Now, there's a computer science. This is the sort of thing that computer scientists can get into lots of discussions about. Which is better for us to show students? Well, of course, the first question is, well, what does better mean? All right, what is it that we want to achieve by showing students this kind of code? So we might ask, would students write better, more correct, more efficient, safer code? Would students be learning more about computer science or the domain? Like here it's about images, but you could imagine it being about something else. Would students become more interested in computer science with one of the notations and the other, or more interested in programming overall and use programming in something else? Now, if we're going to ask any of these comparison questions, We want to, the Latin phrase ceteris paribus, leave everything else equal. Control for all other things which might influence those outcomes. Well, what do those outcomes, those choices include? So what about the math skills of the students? We actually know a lot that students' prior math skills influences a lot about how they think about computer science. In this domain in particular, I would expect that the spatial ability of the students would matter a lot as well. Not just because it's pixels in pictures, but also because you have to be thinking about lists of lists and their positions, red, green, blue, alpha, and the red, green, and blue components to each pixel that make up a color. There's a lot of spatial thinking that's going on here. And who gets access to those good math skills? Who gets access to the good math classes? How do they who develops good spatial ability? It turns out that maths and spatial ability are two things that we actually know how to teach really well. We can give people good spatial ability, but who's getting access to those? How does the teacher's understanding and thus ability to explain these notations matter in terms of the outcomes? We already heard Sue talk about that one of the focuses of the center is to think about teacher knowledge. And obviously that includes computer science, but also their knowledge about things like math, about their spatial ability, and then how do the students relate to the teacher? I thought that one of the really interesting of the 12 principles was modeling what's going on. Does it help for the teacher to model? Well, maybe it mostly helps if you recognize yourself in the teacher. You say, I could do things like that, or that's someone that could be like me. That's an important part of whether or not the teacher's lessons are really effective. Now, what about the community of these schools? Both of these examples that I'm giving you, both the two sets, are about image manipulations. Do images are valued in this school? So, for example, are there art and photography classes? Does art get displayed publicly? Do students work with images in things like journalism or yearbook? Barbara Erickson has worked with teachers who go after the kids working in yearbook and, hey, would you like to write code that crops all those pictures in batch processing or that invents your own image filters? Image manipulation in journalism and yearbook contexts are a way of drawing students into computer science. So do images matter? Now, what if the students would actually understand this code better if it looked like this or like this? So this isn't just a matter of changing the syntax from one set of glyphs or one language to the next. We always teach computer science in stories and analogies, right? In the end, there are no lists of lists or RGB inside of pixels. There's transistors and voltages, but we don't teach in terms of transistors and voltages. That'd be crazy. Well, think about how you translate those stories now into different communities and different languages and different community contexts. I think that's part of whether or not one of these might work over the other. Now, I'm going to add one more notation to the mix, to the two that I've given you previously. I want to talk about the work that we're doing now in teaspoon languages. We're trying to invent new programming languages that can be embedded inside of other than computer science classes, that could be worked with history teachers or math teachers or science teachers. A teaspoon language has to be acceptable to that teacher to achieve their goals if it's going to get adopted. We work at making them highly usable, that these can be learned in less than 10 minutes. We use the phrase task-specific programming to come up with our language. It's a teaspoon language. Put a teaspoon of computing into another subject. I want to show you two of them really briefly. The one, just to give you a sense of what is a teaspoon language about. The second one, we're going to get back to the image manipulation story. So I mentioned that I've been working with history teachers, social studies teachers. This is in collaboration with Tammy Schreiner, who's a history professor at Grand Valley State. In the United States, all history teachers are supposed to teach about data visualization. Very few of them do. As Tammy says, you don't become a history teacher because you love numbers, data, and computers. So I have to think about how do I make data visualization, creating data visualization, make sense in history terms. So the way we do that is in participatory design process. We sit with teachers and say, what is it that you want? So for example, our visualization tool always asks students to identify a driving question, because that's where you start with inquiry in history class. That's what the teachers have asked us for, and so we build it into the tool. We may have the only IDE in the world that asks students first for the driving question, but if you talk to teachers, well, that's the starting place for all kinds of inquiry. So we start with that. We always have two graphs on the screen at once, because history teachers have told us you don't have an interesting historical question until you have two pieces of data, two accounts that disagree with one another. Here what we have is the population of Ethiopia and the population of Rwanda. And the question is, why is there a dip in the population of Rwanda? And we expect students to do a lot of visualization, so we have a space where they can drag their graphs off to the right to save them. If you were to hover over one of those graphs, you would see a little bit of JSON as a script to describe how this graph is created. You may say, JSON, that's a pretty ugly notation, Mark. It is, but we've shown history teachers a bunch of different kinds of notations, and we showed them Vega Lite. And they really like Vega Lite. And we decided, okay, we're going to base it on something that the teachers actually like. If you click on that Customize button, you get to another view of the visualization tool. In this one, you can see still the pull-down menus for specifying the visualization, but what you can also see is the actual script. And if you want, you can edit the script, and when you hit Submit, I both update the graph, but also the pull-down menus. They're multiple linked representations. So to show you that these are equivalent, you can get there from either way, and I'm helping teachers understand the relationship between code and the visualizations they care about. That's an example of a teaspoon language. So let me do the pixel equations one for you now. We developed this working with math and engineering classes in Detroit public schools, where students had to learn to visualize data. And we talked to a bunch of students about what was hard about learning to visualize data. And we came up with a set of learning objectives. The first one was that an equation that describes a section of a graph could also be used to describe a section of a picture. So in this example, what we're looking at is where x is greater than 200, we're going to set all the red values to 255, the highest possible, so they're very red on the right-hand side. The second is that colors can be specified by equations, that you don't just have to have a number between 0 and 255. You could say something like, if the y is less than 200, double the amount of green that is there. And in the third one, we want to show students that they could test a value within a pixel in order to figure out whether or not that's a selected pixel and then make changes to that. So here, where blue is greater than 200, we're going to divide the blue by 2. This, for all of us who know something about programming, would say, well, sure, that's programming, right? The left-hand side is a Boolean expression to choose pixels. The right-hand side, I have the right-hand side of equations for setting the red, the green, and the blue. But I have no for loops, I have no ifs, I have no curly braces, I have no semicolons, I have none of that. All I've got is the mathematics that the math teacher says, oh yeah, that's mathematics. I'll put that in my classroom. But the students are programming, and they're doing image manipulation. Okay. So now I've shown you 3 different forms of notation. These are 3 equivalent programs in the sense that they all generate the same piece of code. They all have the same effect. Consider all the issues that I've laid before you. Student interest, student background, teacher's knowledge, classroom and community context. Think about all of those, but also think about one of the real strengths of the Raspberry Pi Computing Education Research Center. Ages 3 to 19. That's a long time. Maybe we think about more than one language. Maybe we think about introducing things with tools like the teaspoon languages. In a lot of classes, we were the question earlier about the primary versus secondary school. I mean, you could put this in a lot of different contexts at the primary school to get started. And later on, you show us another notation, a little bit more powerful. And a little bit later on, you can finally get to the things like higher order functions and thinking about data structures that are more sophisticated. Over 16 years, you can do a lot of kinds of learning and developmental progressions. At the University of Michigan, I've been working with a project where we want to figure out what is the computing education needed for students in liberal arts, so literature, sciences, and the arts at the University of Michigan. So we had a task force during the pandemic, worked with a bunch of faculty from humanities and media scholars, social and natural scientists. We want to know what future scientists, humanities scholars, and citizens need to know about computing. Now, this is the question we want to know. What is it the students need? But it's not like you can walk up to a student who's never taken any computer science. So what kind of computing do you need, really? So what we decided is to ask the faculty. So I've been now involved in dozens of interviews, surveys over 100 faculty to figure out what do liberal arts and science students need to know about computing. We came up with 3 themes. First is that for these students, so not the students in computer science, not the students in informatics, for these students, computing is about discovery. One of the things that I learned from them is that computational science is different than data science. Data science looks at a great big pile of data and figures out what's there. Computational scientists start with a theory, and they build models, and they fit the data to the models, or they do simulations. It's different than data science. Second is computing for expression. From social media to Pixar, computing has changed the way humans communicate with one another. And finally is computing for justice. Computation pervades everything that we do today. What is that computing doing to our society? How is it impacting us on a daily basis? Okay. And so the new classes that I'm building are computing for expression and computing for justice, and this new image manipulation the blocks I'm building is specifically for the computing for expression course. All right, you may be asking yourself, Guzdial, we heard Sue say it's ages 3 to 19. What are you doing talking about the undergraduates? So let me explain. It's a story that I got from Alan Kay, an ACM Turing Award winner. He was at a dinner hosted by Douglas Adams, and as he describes it, a proper British woman came to him and said, I know you do something about education. I think that it's interesting that you Americans have the best high school education in the world. And Alan was aghast. She says, it's a pity you have to go to college to get it. So my suspicion is that what we consider to be the goals for liberal arts and sciences students may actually be the goals for all of your secondary school students. I expect that you have students who want to be scientists, who want to be artists, who want to be citizens concerned with justice. And what the students want to be in their lives is going to impact how they're going to relate to the lessons that they're shown. Now, those of you who are programmers, computer scientists are saying, wait a minute, what does that have to do with the stories about notation, Guzdial? Because I'm finding that when I talk to students who want to go into social sciences, they want to learn R. And I say to them, well, that's not very type safe. They're like, what do they care? And I talk to the artists, and they say, oh, we use processing. It's like, processing is pretty heavy. It doesn't matter whether or not processing is good language. That is the language of their community. And for me to say, no, you shouldn't use that, is for me to reject their community and what is it that they want to do. So the communities and their goals influence what it is that they're going to learn, what is it that they want to learn. So computing education research is not rocket science. No, it's way much harder, right? Because we know that F equals ma, always, and for all rockets. But humans are far more complicated than rockets. They have all of these other factors. And that's why I come to the conclusion that computing education research is much more complicated than computer science. There's a whole bunch of really interesting computer science topics that we're developing, that we think about, that we worry about, all those that I listed as the two sets of concepts at the very beginning. But if we care about how students learn those concepts, we have to cross those all with what's the student's prior learning? What are their goals? What are the communities that they have? What is the teacher's prior learning, as Sue's pointed out, both conceptual and pedagogical? What's the classroom and school context, their community and culture, their language, and ... There's all kinds of other factors that we haven't even come up with to realize this impacts how students learn computing. These are the challenges of meeting everybody's needs for computing education. And I'm so pleased that the Raspberry Pi Computing Education Research Center is taking on this challenge. It's an important challenge, and there are several lifetimes worth of work to do here. I wish them the best of luck, and I really thank them for taking up this challenge. And thank you for your attention and the opportunity to be here.